And I want to start off with a quote from Francis of Assisi. Since we are here at Francis of Assisi, I thought this was very relevant. Start by doing what is necessary, then what is possible, and suddenly you are doing the impossible. I thought that was very relevant for this entire conference. All right. So let's talk about what the objections are to LE and R. There's several, but I'm going to talk about these four first. First of all, they say the ratio of helium-4 production compared to the excess energy is too high. We get too much helium-4 compared to the energy. Second, you're getting too much helium-4 in the first place. The reaction of deuterium plus deuterium going to helium-4 is just normally a very small reaction. Why do we see so much helium-4? Thirdly, there are no neutrons coming out of the apparatus. That shouldn't be that way. And fourthly, there's no gamma radiation. And as you can see here in this equation, there should be lots of gamma radiation, but we don't see that. Why does this always mean? Let's consider what a hypothetical LENR reactor, which I'm going to use as an example with some very reasonable quantities associated with it. I'm going to say it is producing 1 watt of excess heat. I'm going to start there. I'm going to say in the primary reactions occurring in this reactor are the two usual reactions. Deuterium combining with deuterium to form helium-3 plus a neutron, or tritium plus a proton. Now some of you may not like that. You may say, oh no, that's not right. Bear with me because I'm going to be coming around full circle and explain that. But let's just right now say those are the primary reactions that are occurring. And they occur at 50% ratio for each of the two reactions. Very rarely do we see the helium-4 forming 1 times 10 to the minus 8 when the two deuterium come together. I'm going to say these reactions occur within the palladium core. Let's calculate the power. Find out how many reactions there are if we get 1 watt out. So the energy released is the number of reactions times the energy per reaction. So power, of course, is energy per second. The D2 plus D2 to tritium releases 4.04 MeV 50% of the time. The D2 plus D2 going to helium-3 plus a neutron releases 3.27 MeV 50% of the time. So the average, and I'm going to use this number, is 3.655. So if the reactor core is generating 1 watt of heat, that is 1.71 times 10 to the 12th reactions per second that are occurring in that reactor. And for each of those two reactions is 8.55 times 10 to the 11th reactions for each of those two. In this example that I'm going to be talking about, I'm going to say I have 1 cubic centimeter of palladium and that it is loaded at 90% with deuterium. I'm going to say it is surrounded by a lithium electrolyte in 1 liter of heavy water. I want to talk about how we calculate fusion rates. This is standard. This is the accepted theory, and it's called the Larson equation. And here is a picture of John Larson. He determined, came up with this equation in 1955. This is the equation that is used by the hot fusion reaction engineers in the design of their reactors. This is the accepted equation. This equation has stood the test of scrutiny and of time. F is the number that John Larson used for the fusion rate, the number of reactions per second per unit volume. F is equal to the density of nuclide A times the density of nuclide B times the cross-section of A and B. And that cross-section is energy dependent. That depends on what energy those two nuclides are with respect to each other. And then the velocity, the relative velocity between nuclide A and nuclide B. This is the fusion rate that you would get. So let's plug this into our hypothetical reactor and see what we get. The density of nuclide A is what I'm going to call cold D2. It's the D2 that's sitting inside of that palladium core at 90%. You can calculate what that is. You know the density of palladium, you know how many moles there are in that 1 cubic centimeter. You know at 90% how many moles, how many ions, deuterium ions, there are going to be in that 1 cubic centimeter. And it turns out to be 6.12 times 10 to the 22nd ions per cubic centimeter. It's a huge number. That's, again, as I said, 90% loading. The cross-section is dependent on the energy of nuclide B, and it's obtained from the graph of cross-section versus energy, which I'm going to show in a few slides here. The unit for cross-section is barns, and that is 1 times 10 to the minus 24 centimeters squared is an area, or in meters times 10 to the minus 28 meters squared. The velocity is calculated from the energy, as you can see, the normal equation. First, you want to convert that energy into joules. And then solve for V. You can also, by the way, express energy in terms of the temperature. Nuclide B, what is nuclide B? It depends on what reaction I'm talking about, and in this lecture I'm going to be talking about maybe 10 some odd reactions. So whatever nuclide B is, that's what you put in there. And I want to talk about this funny little equation. What is the density of nuclide B? Well, it depends on how many are created per second. Most of these nuclides are going to be in my secondary reaction, so I'm creating a certain number of nuclides per second. So if I'm talking about helium-3, we just figured out that that reaction occurs 8.55 times 10 to the plus 11 times per second. So that would be the number created per second, assuming I'm getting 1 watt out of my core reactor from the primary reactions. But it's multiplied times the average time spent in the reactor. And in case that's not just real intuitive, I've drawn a little picture. So let's pretend I have a cubic meter box, and I have 5 little objects that go into that box per second, and 5 little objects that come out of that box per second. It's in steady state. Okay, so we're in steady state, but what we don't know is how many of those objects are actually in the box at any one given time. So if on average, if those little blue balls stay inside of the box for an average of 20 seconds, then we can say in steady state they're going to be on average 100 of those little objects in the box at any given time. And that brings up the subject of the difference between thermal velocity and drift velocity. So let's pretend these little blue balls are little bees flying in. They fly into that box. And on average, they stay in there for 20 seconds. So they fly, that would be their drift velocity, they fly 1 meter every 20 seconds. But inside that box, they may be flying around at 100 meters a second. That would be the thermal velocity. So I wanted to distinguish those two differences in terms of the drift and thermal velocity. Now these are the cross-section curves that I use. I like the first one because it gives me all kinds of various reactions. This is experimental data that I got off the web. The references are right there. I like the second one because it has all the lines on it. It makes it real easy to, if you have an energy, you can go up and figure out how much your cross-section is. So these are the curves that I use. Now, let's talk about these secondary reactions. I want to show you a reaction that is that lithium-6 absorbs a thermal neutron. By thermal, I mean room temperature. There's no Coulomb barrier here. And when it does, it breaks. It doesn't absorb, it doesn't capture the neutron. It transforms lithium-6 into an alpha particle and a tritium. Now the cross-section for this reaction is huge, 942 barns. It is enormous. There's no Coulomb barrier. And the abundance of lithium-6 is relatively large, 7.59. When this reaction occurs, it releases 4.783 MeVs. This reaction, this secondary reaction, occurs not in the palladium, but in the lithium solution. This reaction, in case you're wondering, is the reaction they use to breed tritium. It's a very well-known, very well-established reaction, and I have some references there if you want to check them out. Let's do an estimated calculation for a typical example. So, in my lithium, I have 1 liter of water, and I'm going to make that into a cube, 10 centimeters by 10 centimeters by 10 centimeters. It's heavy water, and we know lithium is 7.59% of all the lithium. And I'm going to put 1 mole of lithium, 6 grams, into that water. That would be 79 grams of lithium total in the water. That's a reasonable amount. It's a few tablespoons. I think something like that. A reasonable handful of lithium. But we know, because it's 1 mole of lithium, that there are Avogadro's number, 6.022 times 10 to the 23rd lithium ions per liter. And that changes to 6.022 times 10 to the 20 per centimeter cubed. With a thermonuclear cross-section of 942, then the thermal neutron, for a thermal neutron, I'm going to assume the thermal neutrons here are 100 degrees C. The reason I do that is because I'm assuming the water's boiling when I'm outputting that much heat. Yeah, the water's boiling, it's at 100 degrees C. That gives the velocity for that thermal neutron of 3 times 10 to the 5th centimeters per second. And I know the watt, for every watt generated in the primary reaction, I'm going to have 8.55 times 10 to the 11th neutrons released into that water. Let's calculate, using the Lawson equation, what that reaction is. I'm going to say the reaction, the average time of those neutrons spent in the 1 liter container. On average, they have to travel 5 centimeters, but I'm going to say there's a little bit of that drift velocity. So they're not just zooming out of the container, they bang around inside like those bees did inside that box. I'm going to call that 10 times bigger. So instead of 5 centimeters they have to travel out, I'm going to call it 50. I plug in all these numbers, and I have my density of neutrons, as you can see there. And the fraction, the F rate there, is pretty large. 2.4 times 10 to the 13th. Actually, it's larger than the number of neutrons, so that doesn't work. Basically, I take every single neutron that is produced in the palladium core, it gets involved with this reaction. So the number of neutrons released is 8.55 times 10 to the 11th. 100% of the neutrons are going to be stopped by the lithium solution. The actual fusion rate, F, is actually going to be 8.55 times 10 to the 11th reactions per second. It's going to be the same as the reaction rate in the palladium cell for that reaction that you see here. Now this still takes 100% of those neutrons, even if I decrease the lithium by 1/10 of the amount. Even if the average drift velocity is equal to the thermal velocity, which is very unlikely. It still works. 100% of those neutrons are taken out of the reactor. What do I get? An additional excess power, and I get helium-4. Helium-4 and tritium are produced. Uh-oh, are you going to tell me I'm almost up with my time? I gotta talk fast. Okay. Other secondary reactions in the palladium core. I'm just going to show this real quick because I want you to know I did these reactions. The big thing to point out is that negligible, 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 probably negligible. This last one depends on that drift velocity. The one that's important, though, is this one, D2 to tritium going to helium-4. Again, more helium-4 is created. More neutrons are created. By the way, this occurs in the palladium core, not in the lithium solution. So if more neutrons are created in the palladium core, they go into the lithium solution. They'll get used up in that lithium reaction as well. This one, assuming that I have that the tritium travels 5 centimeters to get out of that palladium core, that would be after it bangs around a few times, I'm going to get 1.82 watts released from this reaction. I get more helium and more neutrons, which again turn into helium and tritium. So on average, and I put that number in blue here because it depends on the actual drift velocity. But on average, you're going to get about 2.82 watts out of the reactor when you consider the secondary reactions. Remember I said the primary reaction is just 1 watt. Consider the secondary reactions. I've almost tripled that. Very good. How much more time do you have? 8 minutes, okay. So for the parent nucleons, or 4 D2 ions plus 1 ion of lithium, I get the child nucleons as seen here. And I get 12.9 MeVs of energy. There's an additional amount that comes from this reaction here. For every helium-4 formed, the above reaction releases 12 MeVs instead of the expected 24 MeVs. And that D2 to tritium makes even more helium-4 and more energy. To sum up so far, I've answered all the criticisms. For every, let's see, the ratio is much larger than predicted. I got it explained here. There's much more helium-4 than a conventional calculation might expect. I've explained it. There are no gamma coming out because I don't have that reaction that creates gamma. And there are no neutrons escaping the apparatus. But let's talk about the big objection to LENR, and that is overcoming the Coulomb barrier. Again, we can recall the Larson equation. But let's consider we've got a lot of energy banging around inside of that reactor. Chain reaction is very probable, and in fact it is predicted, as I show here, that that's going to happen. So the question I want to ask to myself and to you is, could a chain reaction be occurring? What we need is a reaction that can create enough hot deuterium that can overcome that 0.4 MeV Coulomb barrier. If we can create enough hot deuterium inside the palladium core for that reaction to sustain itself. Let's take a look at that. Basically what I'm talking about is, and this is the same as for a fission reaction. This is what the hot fusion guys do. This is how your car engine works. There's no violation of thermodynamics here. I have the total energy released in the palladium core. Some of it gets fed back into the core itself to sustain the reaction. Some of it comes out of the reactor as your heat. So I want to do a rough calculation just to see if it is possible. Can we do this? If I'm going to label my two nuclei as deuterium cold and deuterium hot. And I'm making an average, as we calculated in the previous slide, of 10.2 MeVs. And that does include the tritium plus deuterium reaction. However, it does not include the reaction that's going on in the lithium, because that energy is not going to be fed back into the palladium core. So what I'm going to do is I'm just going to pick some rough numbers and see if I can get a reasonable answer. Let's assume 50% of the energy that the reactor, the palladium reactor, creates is lost as excess heat. And let's assume that 50% of that energy gets fed back into the reactor to create the hot deuterium. That's the remaining 5.1 MeVs. To create what I need to do, I need to create 12 hot deuterium. If we want a 100% chance on average that one of these deuterium will react in a chain reaction, then what I need to do is I need to pick a drift velocity of 1/16 the thermal velocity. How unreasonable is that? Well, it's not. For comparison, if we look at electrons in copper metal, the drift velocity is 2.3 times 10 to the minus 5 meters per second, whereas the thermal velocity is 1.2 times 10 to the 5 meters per second, a ratio of 10 orders of magnitude. No, 16 is not an unreasonable number for what we need for this little hypothetical example, especially since there were a couple of reactions that I mentioned that we're a little bit uncertain about, especially that tritium and deuterium. But what I'm saying here is that this reaction is quite reasonable, and it explains how an LENR reactor can sustain itself. How do we overcome that 0.4 MeV Coulomb barrier? The reactor sustains itself. Yeah, but the big question is how do we, let's see, I'm going to skip through this because I'm running out of time. How do we kickstart this reaction? How does it start? Well, if you take those curves that I showed you before for the cross-section and extrapolate it way down off the piece of paper to, I'm going to call it a D2 that is tepid because it's not really hot and it's not really cold. I'm going to say it's at 100 eV due to the voltage applied to the reactor. I want to know how often that happens. I just need to kickstart it once. Does it happen every million years, I'm in trouble. But, you know, if it happens once a day or so, I'm good. Let's see how often it does. I'm going to pick my numbers, put it into the Larson equation. I'm not going to go through this in detail, but I'll just point out here, it happens roughly 2 times a second. And that's with 100 MeV applied to the reactor. This is a very conservative estimate. I picked 500 times smaller than my extrapolation. All right. Conclusions. The biggest theoretical objections have been answered. Lithium-6 plays a large role. The D2 to T3 reaction is also very significant. The Coulomb barrier is overcome by the reactor's own energy, leading to a chain reaction. The reactor starts due to the applied voltage, 100 volts. Compared to hot fusion, LENR doesn't need as much hot D2 because of the extremely high concentration of D2 cold. It is not necessary to hypothesize any kind of new physics or new type of strange phenomenon occurring in the palladium. We can understand what is going on in the LENR reactor just by using the conventional equations. Let's talk about, this is my last slide. Let's talk about experiments to confirm. With an active reactor, drain out the lithium electrolyte and replace it with non-lithium electrolyte and see what you get in terms of energy, radiation, and child products before and after. Make sure you have lithium-6 in your lithium. Some commercially available supplies of lithium do not include lithium-6. They take that out because they keep it for themselves. After a reactor has started and reached steady state, after a reaction has started and reached steady state, turn down the power, the input power. Because I say you don't need it except to replenish the deuterium. The output generation of excess heat should not go down commensurately. Try various shapes of your palladium core. A thin wire versus a flat disc versus a spherical shape. Which one works best? Another experiment to try is once a reactor is going, turn it off completely, and then try and start it with a much, much lower voltage. Is it going to go? Certainly the heat after death effect, which we all know about. This easily explains the phenomenon. It is a chain reaction occurring inside the reactor, and it's only when we deplete the deuterium that that reaction goes away. Also, look at your palladium core and see if it has numerous visible defects before and after. Is there a correlation to that? And if you have a reactor that won't start, try increasing the voltage and the loading and the surface defects. This concludes my talk. Thank you. Yes, sir.
So on your question about chain reaction involving lithium, lithium-6, as a matter of fact, no chain reaction can be expected.
Why do you say that?
Simply because the next talk of this conference is my one tomorrow morning. Okay, and I did by the way, lithium-based research regarding investigation of cold nuclear fusion. There are products of cold nuclear fusion, such as helium-3 and helium-4, plus heat release. However, there is no other product such as tritium.
Right, but I don't know in those particular reactions.
It doesn't show.
Have we measured to see if those neutrons have been measured?
Well, exactly, no externally neutrons were found with the measuring equipment. Maybe they are inside of the solids, but if they are, I think they are. Because actually, interaction of two deuterium nuclei giving helium-3 must give neutron. But this actually neutron is inside of the solid, and in the end, it has low momentum, or maybe ultra low momentum.
Okay.
Which cannot cause actually some kind of products with interaction with lithium-6. However, I think actually this method is important and it requires further investigation. But I didn't observe any indication of a possible chain reaction in lithium-based alloy, compound alloy.
I have to take a look at your reactor and compare that, and also in my particular example, the sizes, the dimensions, the concentrations I was talking about. So I don't understand. I have to take a look at your reaction.
It's okay, you're welcome.
All right, thank you.
So thank you. I think this is a very helpful exercise to walk through these steps. It wasn't very clear to me what your assumption is with what energy the neutron is born after the DD reaction. Because the literature value, I don't remember it exactly, but it's
3 MeVs.
Yeah, it's about 3 MeVs.
Yeah,
You
but
mentioned
it'll cool down once it gets into the water. So I'm assuming that by the time it gets through the palladium and hits the water, that we've got essentially at 100 degrees C, because I'm saying that the water is boiling at 100 degrees C.
So I think that's an assumption that needs to be further supported. But then also, if that would mean that if we move the cathode very close to the edge, you know, and sort of reduce the amount of electrolyte it has to travel through, we should be able to measure some neutrons coming through the electrolyte.
Right, and that was, I was saying, an experiment to try would be to remove the lithium, or at least the lithium-6 out of your reactor.
But do you think in 30 years people wouldn't have noticed this effect?
That would be one of the other things we can do, is to check the literature. And how many times have people run it without lithium? Not that often, unless it's a dry system. And of those that they ran without lithium, what products did they measure?
So the second question is, I wonder, you know, it would have been helpful to have the neutron capture cross-section at the neutron energy that you assume for the lithium nuclei. So I have the sense, well, no, I mean the neutron capture cross-section for the secondary reaction that you...
Oh, because it's, there's no Coulomb barrier, it's 942.
But so neutrons can scatter or they can be captured, and most
Right.
neutrons would scatter off the lithium nuclei.
No, they get absorbed. It's a huge cross-section.
Well, that would be helpful to show that cross-section to see whether the absorption is actually as high as you allege, such that we wouldn't observe any transmission of neutrons.
Okay, that is what it is. Jean-Paul?
Yes.
Okay, yes. Go ahead.
Okay. Essential part of your report is related to analysis of method optimization of DD reaction. And on slide number 1 and 2 was noted that the cross-section for both channels of DD reaction for creation of proton and neutron approximately the same. From the other hand, it is well known that shown for the first time our friend Mahadeva Srinivasana present here, that the probability of neutron channel of reaction at low energy less but 8 order of magnitude. It's because they present the Oppenheimer-Felix mechanism of reorientation of electric moment. It's lead to practically total suppression of neutron channel. So if we using the linear approximation cross-section from high energy to low energy, it may be not correct, especially in this case.
Okay, then that would just reduce the number of times that the reaction occurs in lithium if the neutrons aren't being generated, right?
No, you see, if there are neutrons generated, it is not necessary to interact with lithium-6. Lithium-6 is doing something else there, which is useful.
Okay, all right. Jean-Paul?
I got the mic.
Oh.
I have 2 comments. I think it's excellent to do this kind of, exercise. But if I understood correctly, you assume 90% V2 of the palladium.
90% low.
90%,
Yes.
yeah. I certainly disagree with that because the deuterium is not D2. It's single D in the palladium lattice.
Oh, I
You
mean,
have
it has-
D2 only in the vacancy. So you should calculate the number of vacancy at the given temperature and take 90% of that one on radius.
Yeah, by D2, I'm not talking about the molecule. I'm talking about the nuclide, deuterium.
Okay.
Yeah,
Okay.
and if you figure out how many deuterium can fit inside of those face-centered cubic,